In the last lecture, we have seen some examples based on the Laplace transform and some queries related to that. Okay, so you have one more query. So we'll solve that query and then we'll go for the next topic. Okay, so let's have your query first and then we'll go for next. Okay, so your query is something like this. Okay, so we have laid f bar of s is equal to 1 upon s minus 3 into 1 upon s plus 3 bracket square. Is that correctly I have written, Shabika?
Yes, sir, it is correct.
Okay, so this is what we want to solve, correct? Yeah, that's good. Okay, so what we have here, so we have to find out the inverse Laplace transform using the convolution theorem. So what we can do is this is f1 bar of s and this is f2 bar of s. Okay, so we have alright. This is f1 bar of s into f2 bar of s. So we have f1 bar of s is equal to 1 upon s plus 3 and f2 bar of s is equal to 1 upon s plus 3 bracket square. Okay, this is going to be s minus 3. Okay, so there is nothing compact rule that this should be f1 and this should be f2. Anything you can consider f1 and the remaining will be f2. Okay, so once we have considered this f1 and f2, then we have to find the inverse Laplace transform of this. So inverse Laplace transform of f1 bar of s is equal to inverse Laplace transform of 1 upon uh, s minus 3. So we know this is e raised to at, so e raised to minus will become plus, and hence it is e raised to 3t. So this is f1 of t. Okay, and now in this case, Laplace inverse of f2 bar of s is equal to Laplace inverse of 1 upon s plus 3 bracket square. So first we have to use the shifting property. So this is e raised to minus 3t because we have plus 3 here, and then it will become s square, and the Laplace inverse of s square is t. So which is going to be f2 of t. Okay, so we got here f1 and we got here f2. Okay, so once we got f1 and f2, and then now we have to use the convolution theorem. So we can say by convolution theorem. Okay, so what we have here, we get. Okay, so what we'll able to get is Laplace inverse of f bar of s is equal to integral 0 to t. So one you have to consider f1 of t and the other you have to consider f2. So here what I have to do is in the first I have to replace this t by u. So I'll be having first function e raised to 3u. Okay, and then second function it will be t minus u into e raised to minus dt minus u and du. So in the first function I have replaced t by u. In the second function I have replaced this t by t minus u. Okay. Now we have to evaluate this. Okay. So simplify integral 0 to t. This is going to be e raised to 3u. Okay. And this is you'll be having t minus u e raised to minus 3t e raised to 3u and 3. Okay. Now we have integral 0 to t. So this is going to be t minus u. Okay. Then we have e raised to minus 3t, e raised to 6u and du. Okay, so here what we know is this e raised to minus 3t is going to be constant. Okay, because we are integrating with respect to t, with respect to u, so t becomes constant, and hence e raised to minus 3t you can take out 0 to t, t minus u, e raised to 6u du. Okay, and now we have to integrate this. Okay, so let us integrate e raised to minus 3t. So this is u into v rule. Okay, this is going to be u and this is going to be v. So u remains as it is, t minus u. The integration of v, e raised to 6u on 6. Okay, minus the derivative of this u. So it is going to be minus 1. And integration of this term. So e raised to 6u upon 6 square. And the limit is 0 to t. Okay. So e raised to minus 3t. Here we'll be having 1 by 6 e minus u e raised to 6u minus minus plus 1 by 36 e raised to 6u and 0. Okay. Now let us apply this value. So e raised to minus 3t 1 by 6. If I put t, so t minus t is going to be 0 plus 1 by 36 e raised to 60 minus. We are using lower limit, so that's why minus. I am putting the value of u. So this is going to be 0. So 1 by 6 into t and then e raised to 0 you have. So it is going to be 1 minus 1 by 36 and this term. If I put u is equal to 0, it's going to be 1. So that's what we have. Now simplify e raised to minus 3t. This term is 0. So what you got here? See. So it is 1 by 36 e raised to 6e minus 1 by 6t minus 1 by 36. Okay. And now apply this multiplication. So we can have, I can have 1 by 36 common. So I'll take 1 by 36 common. If I multiply this e raised to minus 3t and e raised to 6t, so I'll get e raised to 3t minus e into e raised to minus 3t. And here we are taking 36 common. So here I'll be having 6t e raised to minus 3t. And this is e raised to minus 3. Okay. So again what you can have is 1 by 36. This is e raised to 3t. Okay. Minus e raised to minus 3t minus 6 e into e raised to minus 3t. So what I know for this? Okay. So we have hyperbolic sine of x is equal to e raised to x minus e raised to minus x by 2. And hence 2 hyperbolic sine x is equal to e raised to x minus e raised to minus x. So this is 1 by 36 and by having 2 hyperbolic sine of 3t minus 6t e raised to minus 3t. Okay. Again, what you can simplify, you can cancel this 2. So this is Laplace transform of f power of s. So you got Laplace inverse of power of s. What will be having 2 you can have common. So I'll be having 1 by 18. Then I'll be having sine hyperbolic 3t minus 3t into e raised to minus 3t. Okay. So this is what you'll be having inverse Laplace transform, or you can have the inverse Laplace transform of 1 upon s plus 3 s minus 3 bracket square. Okay. And this is what you'll be having 1 by 18 Rolex sine of 3t minus 3t e raised to minus 3t. Okay, that's what the example. Sorry. Okay, so you change here. This is going to be the first term is minus and the second term is plus. So here you have s minus 3, s plus 3 bracket square. That is how we are able to find the inverse Laplace transform using the convolution. So I hope is your doubt clear now? Have you got what we have solved? Okay, so the steps that we have followed. So is that clear now? Is that okay? Welcome. Okay. So is there any other doubt? If you have any other doubt, you can ask. No problem. Okay. So you can, yeah. The answer up to exponential term is also satisfactory. Yes, it is satisfactory. See, when you are told to prove that, okay, then definitely you have to prove that. But try to simplify as much possible. Okay, so this is one thing that you always need to understand. Try to simplify as much possible. Okay, so when you got exponential term, that's okay. Okay, but if examiner wants you to simplify up to the hyperbolic sign terms, then you need to understand. Okay, so suppose you got answer up to this, that's okay. You got answer, that is okay. But if examiner wants this answer, then this answer will not be sufficient. So one or two marks will be reduced. But if you know, then why we have to lose 1 or 2 marks? Okay, we have to write all the answer and then simplify as much possible so that you will get full marks. Okay, so always try to simplify as much possible so that you will not miss your marks. Okay, okay, great. Okay, so now, is there any other query? If there is any other query, we can take that. Or, we'll move to the next topic. So fine. I hope then there is no query. Okay, you understood this. Good. Okay. So fine. Up to yet, what we have seen in the statistical technique is that we have seen how to find out the relation between the data if we have the relation or not, and then up to what percentage of relation we are confident of. Okay, that we have seen. Okay, what are the claims under Fourier series? Okay, so the claims under Fourier series are like that. What is the sum of 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square plus 1 upon 4 square plus 1 upon 5 square plus 1 upon 6 square plus 1 the term? What is the summation 1 upon n square? Quickly. So it is 5 square by 6. Okay, these are the claims. Okay, if I have odd terms, okay, 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus 1 upon 7 square, so on that up. So this is the series summation 1 upon 2n minus 1 bracket square. What is the sum for this? So it is 5 square by 8. Okay, so this kind of claims we will have. Okay, and so yeah, we can have this kind of claims. These are called claims. Okay, so the series and the claims based on that series particularly. Yeah. Is there another query? Okay, no problem. That's great. So we have seen the different techniques of. There will be questions. Otherwise, you can unmute yourself and then ask your question. It will be a better one.
Sir, will you be given questions where will be given the Fourier series, but there will be a hence part. We have to just prove the hence part.
No, directly you will be asked the hence part. Okay, or you will be asked the question based on evaluation. So that means you will be asked A0, what is A0, what is AM, what is BN, or what is going to be, for example, I want to find out what is the value of A5. Okay, so A5, A4, anything will be asked you where you have to calculate it. And that's why in our examination we'll have less questions, okay, than other subjects, because here you need to calculate the terms.
Okay, sir.
Yes. Is there any other query? If there is, then we will take it, or otherwise move on the next topic. So shall we move on to the next topic now? Okay, we'll move on to the next topic. Okay. So now we have seen the different techniques of data analysis, starting from the correlation coefficient, rank correlation coefficient. Then we have studied the regression, and after that we have studied the linear regression and the non-linear curve fitting. Okay, so it is also called as non-linear regression. Okay, so this is what we have when the data is given. Okay, now we have to move on. Okay, what are the chances of happening anything, or what are the chances that we are correct? Okay, or what happens when you see you have studied the graph theory and you have studied the minimal path also. Okay, so what that means in a real life? Okay, that's we need to understand first. Okay, so these graphs are nothing but the networks for us. Okay, or we call them as topology. Okay, so these are the networks or the topologies for us. And then there are two types of networks, wired and wireless. Okay, so most of the time, so we use wireless nowadays. Okay, wired also we use. But how we lay down this network? So we lay down any network in such a way that the chances of miscommunications are nearly zero. Okay, now how the chances of miscommunications are nearly zero? Okay, so we can see an example. Okay, so let's have an example. Suppose we want to send a message to our friend. Okay, and we are using Airtel mobile phone. Okay, and the our friend is using Vodafone mobile phone. Okay, so other than Airtel. Okay, and now we want to send a message to him. Then how this message will transmitted, or how this message will travel, and what are the path or what are the networks this message will follow. Okay, so suppose when we send a message, we are sending from Airtel, also from Airtel, it will go to the nearest cell, okay, or nearest tower from our mobile phone. Then from the tower, it will go to the Airtel hub or Airtel server. Then from the Airtel server, it will go to the central hub or central server. Then from the central server or hub, it will go to the Vodafone hub or Vodafone center. And then from the Vodafone hub, it will go to the nearest tower or nearest cell to the particular friend or where our friend is. And then from that cell or hub or tower, that message will be delivered on its mobile. So you can see what are the path that message has followed. Okay, so it has followed from handset to nearest cell or tower, then cell to the service provider hub or center, then central center, and then from central to the Vodafone hub, then from that the nearest cell or hub, and then to the handset of our friend. Okay, so this is the path. Okay, and now you can have your different algorithms to find out this minimal path, like Preem-Dijkstra's algorithm and all. Okay, now see what are the chances that this particular message will not be delivered to the correct person. Or in other words, what are the chances that the communication between the source and the destination will fail? Okay, so the message is not delivered, that means it's a failure of the network. Okay, or a failure of the task. So, what are the chances that the task will be a failure? Okay, so if you see, it rarely happens, or I can say hardly happens, or I can say the chances of happening this thing is nearly zero. Okay, so it is nearly zero unless and until the network is down. Okay, or there are the problems in the network. Only then the message will not be delivered immediately. It will be delivered when the network will be restored. Okay, but the chances are it will be definitely delivered. Okay, and hence we have to think of the chances. Okay, so definitely the chances of not deliver or the chances of failure are going to be zero. Okay, and this gives you the success of this particular network or the particular technology. Okay, so as you are all IT students, so when we think of our software, okay, so uh, how many times your software crashes? Okay, so hardly any time. Okay, so we cannot say it will not crash. Okay, but hardly it will crash. So the chances of failure of a software are rarely or nearly zero. Okay, so why this happens? Okay, so what is the procedure that these chances are rarely or these chances are zero? Okay, so what happens when we develop any software? Okay, see, we start with the developing phase. So first we want to make the algorithms that what we want from this software, and then how we are able to get this from the software. Then one layout is made, okay, and after the layout, it is given to the developer team. So developer team develops that software, and then after developing the software, it is given to the testing team. Okay, so what this testing team does? Okay, so this team explores that software for the different functions. Okay, and it tests that software for the different types of queries, different types of executions, different types of reports, and all. And it tests for how many failures are there. Okay, or when the software is not giving the proper answer or the proper reason. Okay, and when the software testing team is assured that it is not giving any failure or there are no more failures, okay, in several testings, and this testing is done in thousands of times. So it's not just 10 or 20, it is done thousands of times. Okay, and then after testing the software thousands of times, when there is a rare failure, or we say the chances of failure are nearly zero, then this software is made available for use. Okay, so this failure we have to reduce, and reducing the failure, in other word, is nothing but building a trustworthy software or building a trustworthy game or building a trustworthy output. Okay, and that's what is required. And to test this all, we need to understand the probability. Okay, these chances are nothing but the probability. Okay, so we need to understand this concept of probability and how this works, or what should be the probability to approve any software to go in the market. Okay, so when this probability of approval is required, so normally we calculate the probability of success and the probability of failure. Okay, or one you calculate, then other you know easy. Okay, so when these probabilities are very good and we are confident enough. Okay, so again, for the confidence, what we have to do is we have to consider the probability of success and the times of dry run. Okay, dry run means without giving the actual data, we work on the data. So the probability of the success and the probability of success and the number of runs, if we consider the relation between this, and we get the correlation coefficient. So if this correlation coefficient is sufficient, that means if it is more than 9.99, okay, then we can say the software works in a good manner, and then we can trust that because we have 99% confidence that yes, it will work on any query, and then only we can allow it to go into the market, or we will allow it to sell, or we will approve it for functioning. Okay, so this is how the things are related. Okay, and that's why we have studied first how to test the confidence, and now we are testing how to generate the data. Okay, or what data we will be testing. Okay, so this is how we need to understand the probability first. Okay, and then we can think of the next. Okay, so the chances of failure, the chances of success, these are all probabilities. Okay, so when we design any network or when we lay down any topology, or when we design some, then we always have to consider what are the chances of failure and what are the chances that in some failure also we can work. Okay, so may possible in computer networks or in other, you might have come across about this term, the networks or the topology, or may possible you will come across some in other subject you will come across with this word called topology or networks. So in mathematics we call it as topology, in applied manners we call it as network. So we have to design a network such that suppose any one of these hub got failure. Okay, so see the example of the message, sending the message. Suppose my Airtel, one of the Airtel hub is not working, then what are the chances that my message will be delivered? Okay, so while designing this, okay, so Airtel will always take care that there is another way which will be available for the masses to communicate. Okay, and that's why these networks are designed in such a way that probability of failure is very less. The chances of failure are very less. Okay, and that's why while designing this, we need to understand how many minimum number of nodes I should put so that my network will be a never failure. Okay, so what is the question? How many minimum numbers of the hubs I have to put so that my network will never fail? Okay, and according to that we have to work. Okay, or deciding of the communication nodes over a network. Okay, how many customers you have in that particular area, and so that what will be the capacity of each node, how many customers it can handle in the particular area, and then how many minimum number of nodes I should put so that I should able to manage the overflow, because it may happen sometime in the node may be overflow. Okay, so we should able to handle that more than the capacity uh, consumers or customers arise at any point of time. Okay, and so the need we should able to fulfill, and so that we will have some number. So this is always decided by using the probability, and that's why we need to understand the probability. So basic concepts also you have seen some of the basic concept, but we'll revise that basic concept and then we'll go for the next questions or the next concept of this probability. So let us revise first the basic things. Okay. So here we are done with this. Okay. Uh, Now we'll see our concept. Next concept, probability. Okay. So to understand the probability, we need to understand first the random experiment. Okay. So what is meant by random experiment? Okay, so what is going to be a random experiment? Okay, when we know what will be or what will happen, but we are not certain about happening of that thing. Okay, so this is called the random experiment. Okay, so for example, there are some classical random experiments. So classical random experiments are the coin tossing. Okay, then throwing a die or rolling a die, and then playing cards. Okay, so these are the three classical examples of the random experiment. Okay, because when we toss a coin, we know either head will be there or tail will be there. Okay, so definitely it is either going to be head or it is going to be tail. So head or tail we know, but we don't know when we toss a coin whether we'll get only head or whether we'll get only tail. Okay, so if I toss a coin, I'm not sure. So that means outcome is known but uncertain. Okay, so what we have, outcome is known but uncertain. we cannot guarantee that outcome will come. Okay, so same thing about rolling a die. Okay, so a typical die has 6 faces. It is numbered from 1, 2, 3, 4, 5, and 6. Okay, so this die has 6 faces, and the 6 faces are numbered from 1 to 6. So that means if I roll a die, I know that there will be some number out of this only. Okay, but I am not sure which number I will get. Okay, so I know what will be the number. It will be either one of this 1 to 6, but I am not sure what number I will get, and that's why the outcome is uncertain. Okay, and that's why this is also called as a random experiment. Now, in playing cards, okay, if I want to pick any card out of this 52 card, I know it will be one of these 52 cards, but I am uncertain that which card it will be. Okay, that's why these are the classical numbers or classical examples in probability theory. Okay, so when we start probability theory, we always start with this classical examples. Okay, so let us write the definition of the random experiment. So we have the random experiment as experiment with known outcomes, but the chances of getting a particular outcome are uncertain. Okay, or getting a particular outcome is uncertain. Okay, is called a random experiment. Okay, this is called as random experiment. Okay, now the next thing that we need to understand is sample space. Okay, so here we have the random experiment. So once we perform the random experiments, then we have the outcomes of this random experiment. So if I collect all the outcomes, then it is going to be the sample space. Okay, so what is the sample space? Sample space is the collection of all outcomes of a random experiment is called sample space. Yeah, so that's what we have. The sample space is denoted by capital letter S. Yeah. Now we have sample. Yeah. So what we have the sample point. So we have the sample space. So what will be having the outcomes of the points elements of sample space are called as sample points. Okay. So the elements of this yes or the outcomes are called sample points. Okay. So once you have the sample point, then we need to understand what is event. Okay, so what we have here all the outcomes. So what we can say is the favorable outcomes are called, or the set of favorable outcomes. The set of favorable outcomes is called an event. Okay, so it is called an event. So how I can decide the set of favorable outcomes? For example, there is a coin tossing game, and then if I expect X to be, or this to be head, then we say it is an event. Okay, so we have this set of favorable outcomes. This is the event is a subset of sample space. Okay, what we can say, event is a subset of sample space. Okay, but this subset may be proper or improper. Okay, so you know about the proper and improper subsets. Okay, so when I say the event is a subset of a sample space, so it may be proper event, it may be improper event. Okay, so proper subset is what, which will not be yes or five. Okay, so improper subset are the empty set and the set itself. Okay, so here what happens if I have event to be empty set? Okay, so when we have no sample points in the event, then the event is called as null event, or it is called as impossible event. Okay, so for example, we are rolling a die, and then after rolling a die, we want to get zero. Okay, so is it possible? Is it possible to get a number zero when we roll a die? No. Okay. So that's not possible. That means it is going to be an impossible event, or it is a null event. Okay. Is it possible to get a number who is more than square of the number more than 3? So is it possible to get a number which is square of a number more than 3 when we roll a die? No. Okay, so definitely not, because if I want to get a square, then what are the square when we roll the die? Square is 1, so it is square of 1, then it is 4, the square of 2. But if I think of 3, then it will be 9. So is it possible that you will get 9? No. Okay, and that's why these are called impossible events, or these are called null events. Okay, so this is the improper set. Now, another improper set is the set itself. Okay, so when I toss a coin, okay, then I may get head, I may get tail. Okay, so getting head or tail is another event. So which is the whole set or the sample space itself. Okay, so these are the improper subset. Otherwise, it is going to be a proper subset. Okay, now once we have the events, okay, then how we are able to find the probability of this event. Okay, so we know the sample space, we know the event, and now we are able to define probability of this event. So we'll see the classical definition of the probability. Okay, so now we are ready to define the probability. Okay, so after defining the sample space and the event, we are able to define the probability. So let us define the probability. Okay, so let us define the probability. What probability we have? Okay, so here what we consider let S be the sample space of a random experiment, and n of S is equal to m. P the number of sample points in S. Consider A, B, the event of the random experiment with sample space S. So that means if A is the event of the random experiment with the sample space S, means A is the subset of S. Okay, so as we know, the event is the subset of the sample space. Okay, so I can write that is the event is subset of sample space. Okay, so here the event is going to be the subset of the sample space, and now we define the number of points in A. Okay, so let n of A equal to M, we assume be the number of sample points in A. Okay, then probability of event A is denoted by E of A and is defined. So what we are able to define as the ratio of number of sample points in A to the number of sample points in sample space S. Okay. So that is, but we have the probability of any event A is equal to number of sample points in A upon number of sample points in S, and this we can have M by N. So this way we are able to define the probability for any event. Okay, so this is how we are able to define the probability for any event. And once we know the probability for any event, then what are the things related to the probability of any event? So these are the remarks that we need to understand about the probability. So what we can have is for every event A, we can write, so for every event A, 0 less than or equal to probability of A less than or equal to 1. So for any event A, the probability is always in between 0 to 1. So either it will be, but it will never be less than 0, and it will be never greater than 1. Okay, so these are the basic things that we need to understand. Probability is always positive. Okay, so you can see this ratio. The number of elements in any set is always positive, and here the number of elements in S is always positive. So the ratio is always positive. So that's why it will be always greater than 0. It will be positive, but less than 1. Okay. Now the question is when it is going to be 0 and when it is going to be 1. So next, if A is a null event, null, or we can say impossible event. Yeah. Then probability of A is equal to 0. And third, now if A is equal to S, Okay, see here A is going to be yes. So number of points in yes upon number of points in yes, and it's going to be 1. Okay, then we have probability of A is equal to 1 is equal to probability of sample space. Okay, so we can understand the probability of sample space is going to be 1 always. Okay, next we consider collate A1, A2 up to AK. Okay, B the mutually exclusive events of random experiment with a sample space S. Okay, so mutually exclusive means what you're having. There are two things. Okay, AI intersection AJ is equal to phi when I is not equal to J. That means these are all disjoint. In other way, we can say these are all disjoint events. Okay, so if these are all disjoint events, then what we have. Okay, so then we have the probability of, we can say summation of probability of AI is equal to 1 when I is running from. So when we have this mutually disjoint sets, then and their union is going to be the sample space. Yes, then the sum of the probability of all sets or all events is going to be 1. Okay. Now we can have the next. Suppose they are not disjoint, then what? Okay, so let A and B be the events of sample space. Yes, then okay. Now I'm not mentioning that they are mutually disjoint. So what will be having the probability of A union B. So this is how you can see this events. So this is event A. Okay. So this is event A, and this is event B. Okay. So what you can have is this is one of the part. Again, this is the other part. Okay, that's what we have, and this is going to be the third part. Now I want to find out the probability of A union B. So what is having probability of A plus probability of B? But when I say probability of A plus B, then this part I have considered in A also, and this part I have considered in B also. And if I am considering this part rate per price, so I have to subtract these per types, which is A intersection B. So this section is A intersection B. And this is how we can have the probability of A union B, which is probability of A plus probability of B minus probability of A intersection B. Okay, so these are some of basics of the probability that we have to consider. Now we consider our classical examples. So first example is coin tossing. Okay, so when we have a 1 coin toss, so what will be the yes? The sample space will be either head or tail. Okay, second, if we consider the rolling of die. Okay, suppose we consider rolling of die, then what will be the sample space? Will be having 1, 2, 3, 4, 5, and 6. So this is going to be the sample space. Okay, and the third classical example that we consider is playing cards. Okay, so we need to understand this playing cards. So how many of you know the playing cards? Any of you know the playing cards? Any of you know playing cards? Yeah, Gaurav knows. Good. Akhilesh. Yeah. So, can any one of you unmute yourself and then explain this playing cards? So you can unmute yourself and then explain the playing cards. Any one of you? Yeah, Advait, you can unmute yourself and then explain this playing cards. Advait,
So there are 52 cards and two colors, red and black, and there are four card types: spade, club, and heart and
okay,
diamond.
good,
Then there's ace, king, queen, jack, and in some there's the joker
okay,
card.
okay. So Joker, we do not count. We count only 52 cards for our random experiment. Joker is very fishy. Okay, so it can have any value. So that's why we don't calculate, we don't count that card. Okay, so the basic of this we'll see is what we have. Okay, so we have 52 cards. Okay, and in that 52 cards, so let us try to understand this 52 cards. Okay, so we have 52 cards. We call it as pack. Okay, so what we have in this 52 cards? Okay, we have basically if I differentiate this between the cards on the basis of color. Yeah, then we have red color cards which are 26, and we have the black color cards here which are 26. Okay, now in this red and black, again we have two types of cards in black. Okay, so we have 13 here. Okay, so what are the cards we have? We have clubs and spades. Okay, so we can see the clubs like this, and we have uh, spades like this. Okay, then in paid cards. Okay, so we have here 13 two sets of 13 13. So these are diamonds and hearts. Okay, so diamonds we have parallelogram. Okay, or we can say a rhombus. Okay, and then for hearts we have a heart shape. Okay, so these are the four types of cards we have, and in each set of this 13 cards. Okay, so we have these 13 cards as. Okay, so first we have S. We consider 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, and then we have this Jack, Queen, and King. Okay, so these cards, okay, are called number cards. Okay, and these cards are called face cards, or these are also called as picture cards. Okay, so there is a face or picture to these cards, Jack, Queen, and King. So these are called face cards or picture cards, and these are all called number cards. Okay, so Ace has no face, so that's why it is counted as the number card. Okay, so this way, what we have in the 13 cards, we have 10 plus 3. Okay, so 10 number cards, and this 3 are face cards. So in the 52 cards, again, we have 40 number cards and 12 face cards. Okay, so these are the basics of understanding these three random experiment. So coin tossing, we are add and tail. So we can toss one coin, two coins, three coins, and accordingly we can write the sample space. We can roll one die, two dice, and three dice, and accordingly we can write the sample space. In playing cards, we have 52 cards, and then we can have the different combinations of this. We may have color combinations. We may have the face and number card combination, and then we can use the different combinations. See, up to this coin tossing and rolling a die, you are able to write the sample space. So it becomes easy to count the number of sample points. But when we go to the third experiment, okay, it becomes difficult to write the sample space. And that's why we go with the concept of permutation and combination. Okay, so here we need the concept of permutation and combination for the third experiment.